Okay, so another problem about moment of inertia and rotational kinetic energy. So we have a system of point particles shown in the following figure. Each particle has a mass of 0.3 kilograms, and they all lie on the same plane. Part A says, what is the moment of inertia of the system about the given axis? So our moment of inertia, I, is the summation over I of mi r sub I squared, where m is the mass and r is the distance from the axis of rotation. So let's just say, for example, this is m1, this is m2, and this is m3. Then this is r1, this is r2, and this is r3. So then our moment of inertia is, and while we're at it, before I actually do this, it says each particle has the same mass. So m1 equals m2, which equals m3, and we're just going to say that's equal to m. So I is equal to m r1 squared plus m r2 squared plus m r3, not cubed, squared. And if I wanted to, I could factor out the m since they're all the same. r1 squared plus r2 squared plus r3 squared. And that's your moment of inertia. Now part B, it says, well, if it's rotating and it gives us an omega of 5 revolutions per second, what is the rotational kinetic energy? So the first thing I'm going to do before I forget is convert this and make note that 1 revolution is equal to 2 pi radians. So that drops 10 pi rads per second. And then what it really wanted was kinetic energy rotational, which is 1/2 I omega squared. And in the previous part, we solved for our I. We know that it's m times r1 squared plus r2 squared plus r3 squared times omega squared. So that's 10 pi squared. And that's your total rotational kinetic energy. So I'll box this. This is a pretty important equation to know, rotational kinetic energy. And then I'll box this as well, because that's how you find your moment of inertia. So hopefully that helps a little bit with moment of inertia and rotational kinetic energy.